Last time we started with a discussion of the Ginsburg Landau theory of the superconducting phase transition. Today we will discuss this in somewhat greater detail, because as I already said, the Ginsburg Landau theory is of great importance whenever one considers the thermodynamic aspects of the superconducting phase transition, and these aspects are of paramount importance whenever we consider a superconductor for technical applications. Now, the Ginsburg Landau theory is a variation of the much broader theory proposed by Landau in order to explain any phase transition in different thermodynamic systems. The basic formalism goes by discovering an order parameter of the transition. So, the step 1 in all these theories is to specify an order parameter. It is 0 for temperatures above the transition temperature, but not 0 for temperatures below the transition. So, this is the basic definition. Any parameter which has this property can be used. We explained last time that the magnetization in a ferromagnet can be, for example, the spontaneous magnetization can serve as an order parameter. Similarly, the spontaneous polarization in a ferroelectric, or in the case of the superconducting state, we know the concentration of superconducting electrons, concentration of superconducting current carriers. Charge carriers can serve as an order parameter, because there are no superconducting charge carriers and the concentration is 0 for temperatures above the superconducting transition temperature, and it is non-zero for temperatures below the transition temperature. And we already said that the superconductor is a quantum mechanical state. Superconducting state is a macroscopic quantum state. Therefore, with a wave function psi, which may vary as a function of the spatial coordinate. So, this is such that this concentration is proportional to mod psi of r square. The square of the modulus of the quantum mechanical wave function is a measure of the charge concentration. So, the Ginsburg Landau theory starts by identifying this, the order parameter, as the macroscopic wave function, its modulus square, and then expands. The second step is expand free energy density in the ordered state in powers of the order parameter. Thus, if Fs is the free energy density in the superconducting state, this is equal to Fn in the free energy density in the normal state plus alpha psi square plus beta by 2 psi power 4 plus etc. To be clear, this since psi of r is a function of the position vector r, you can also have a kinetic energy density which is given as, this is the expression for the momentum in the presence of an applied magnetic field whose vector potential is A. The applied magnetic field by Maxwell equation is given by the curl of the vector potential. So, this is the kinetic energy density, and then you can also have in the presence of a magnetic field a magnetization term. So, all these together give you the total free energy per unit volume. Well, I can write this like this. So, to keep the discussion simple, let us first go in steps and remove the field dependent terms and consider the situation in zero magnetic field. So, in that case, I write lowercase letters to show that it is the free energy density. Now, alpha and beta are constants. To be chosen by the theory. So, if we remove these terms involving the kinetic energy as well as the magnetic field term, then we simply have Fs minus Fn equals alpha psi square plus beta by 2 psi power 4, neglecting higher order terms. So, if we take this, and the third step is to minimize the free energy with respect to the order parameter, in this case psi or equivalently psi star, since psi mod psi square is psi star psi. So, we can minimize it with respect to variations in psi or equivalently with respect to psi star. So, if we do this, we end up with an equation like this. Minimize it means set the derivative with respect to that parameter equal to 0. So, this gives me so this has two solutions, either psi is 0, in other words there is no order. So, this corresponds to the state situation in for temperatures above the superconducting transition, whereas below the superconducting transition psi is not 0, and therefore alpha plus beta psi square equals 0, which gives me psi square as minus alpha by beta. This automatically says this is related to the concentration of charge carriers, and it is a positive definite quantity. Therefore, if beta is greater than 0, alpha is less than 0, in order that this is positive definite. So, I can write therefore this as mod alpha by beta. Having got the condition for minimum, free energy minimum, let us plug this in the free energy minimum expression, and this becomes Fs minus Fn corresponding to the minimum is alpha into my alpha, well let me write minus alpha by beta plus beta by 2 into alpha square by beta square, which gives me minus alpha square by 2 beta. Now, we know that the free energy minimization takes place via the critical thermodynamic critical magnetic field, and we know that the Fs minus Fn is actually Bc square by 2 mu naught. We already discussed this, where Bc is the thermodynamic critical field. Critical magnetic field. So, in terms of the Ginsburg Landau parameters, we therefore get alpha square by beta equals Bc square by mu naught. That gives me an expression for Bc square as mu naught alpha times alpha by beta. And we also know that the London penetration depth is ms by mu naught ns qs square. So, we can see that the thermodynamic critical field as given by the Ginsburg Landau theory can be related to the London penetration depth. The Ginsburg Landau theory goes further and talks about also the variation of the spatial variation of the order parameter, and we can minimize the free energy also with respect to the spatial variation of the order parameter. For example, our discussion here can be regarded as the situation deep within a superconductor, where the order is already fully established. But when we come to the interface between a normal and superconductor or the surface of the superconductor, then the order develops, and it may be expected to develop over a certain length in space. So, there can be spatial variations to the order parameter with associated changes in the kinetic energy density as given by so this is the kinetic energy density. If we still take B as 0, the applied magnetic field, this simply gives me minus h cross square by 2m d square psi by dx square in one dimension. For a one dimensional superconductor in 0 magnetic field. So, if I take this, then the equation becomes this is the difference in free energy, and if we take this and minimize it with respect to the order parameter, then I get an equation like where psi is different from the value of psi deep within a superconductor. Let us call this psi infinity. So, this means let us say the actual wave function here is psi infinity times some parameter f. So, that psi infinity is constant deep within this. So, d square psi by dx square really becomes psi infinity times d square f by dx square. So, I end up with an equation like after minimization. Now, this cancelling psi infinity throughout. Therefore, now let us say f is slightly different from this, is really psi by psi infinity. So, deep within the superconductor this will become f equal to 1. So, let us say f at the interface is something like 1 plus g, where g is a small compared to unity. So, that g is a measure of the order. So, that in terms of g we get an equation for g, which is the form d square g by dx square minus 2 g equal into 2m alpha by h cross square g equals 0. So, all these are constants. So, let us say 2m mod alpha by h cross square, since this is an energy. So, these are the dimension reciprocal length. So, let us call it with a subscript GL to show that it is a length defined by the Ginsburg Landau theory. The psi GL is known as the Ginsburg Landau coherence length. So, with that nomenclature I can write this as d square g by dx square minus 2 by psi square g equals 0, for which the solution will be g equal to g is of the form exponential minus x root 2 by psi. So, what is the physical meaning of this? This means that the order given by this develops and decays in a with distance in a way with a characteristic length of the order of the Ginsburg Landau coherence length. So, that means that the interface of a superconductor, normal to superconductor interface, we have the order building up. There is no order here. So, this is 0 and then the order builds up over a characteristic length of the order of the coherence length. So, this is how the order develops, and then this goes to its full value psi infinity here deep within the superconductor. So, the Ginsburg Landau theory deals with a situation which is at the surface of the superconductor, where the order develops from 0 to and builds up to its full value deep within the superconductor, and the length scale over which this order develops is called the Ginsburg Landau coherence length. So, the Ginsburg Landau coherence length is another length scale which is discovered by this discussion, and in addition to the London penetration depth. This is a very interesting situation, because we now have two length scales. One is the London penetration depth which says how the magnetic induction field goes and penetrates the superconductor and how this is excluded. So, this is at the full value and it decays like this over a length scale with a characteristic length which is known as the London penetration depth. So, this is the full value and this is how it decays. That is one length scale. The second length scale is the Ginsburg Landau coherence length, and it describes how the superconducting order at the interface develops and builds to its full value deep within the superconductor, and the length scale characteristic of that is the Ginsburg Landau coherence length. Now, when a magnetic field penetrates, the magnetization gives rise to a increase in the free energy, whereas the order developed over a length scale of the order of the Ginsburg Landau coherence length gives you the free energy decrease because of the evolution of the order. So, these two are competitive processes, one contributes to an increase in the free energy, another contributes to a decrease in the free energy. So, the total of these two contributions decides the relative balance of the normal and free superconducting free energy densities. Therefore, suppose you have a material, this gives a convenient way to classify the so called type 1 and type 2 superconductors. Now, we already saw that a type 2 superconductor is one in which there is partial penetration of magnetic flux in the field region between the lower and the upper critical fields. We saw that the magnetization graph goes like this in the superconducting state and then goes like this. So, this is B. So, this is 0, this is negative value. So, this is Bc1 and this is Bc2. So, in the region between Bc1 less than B less than Bc2, this is the mixed state. This region is the superconducting state, this is the mixed state, and the region beyond this is the normal state where the penetration of flux is complete. So, in the mixed state, this is the behavior of a type 2 superconductor, whereas the behavior is just this for a type 1 superconductor. So, this is Bc, this is type 1 behavior, this is the superconducting state, this is the normal state. So, the flux is excluded in this region with a negative magnetization, and then at the thermodynamic critical field the flux penetrates completely and the material is driven normal, whereas here you have a region of range of field values between Bc1 and Bc2 in which the superconducting and normal regions coexist. So, there is partial penetration of magnetic flux. So, the Ginsburg Landau theory now gives us a way to understand how the superconducting and normal regions can coexist in the mixed state, because it basically reduces the problem to one of the free energy minimum when you try to produce an interface between normal and superconducting regions. A mixed state of this kind will be possible only if it is energetically favorable to produce such interfaces where the normal and superconducting regions are separated by a surface. This is possible thermodynamically only if the free energy is lowered in effect by the creation of such an interface. So, essentially we saw that the free energy balance is determined by the two length scales lambda L and psi g L, the London penetration depth and the Ginsburg Landau coherence length. So, the Ginsburg Landau theory gives us a criterion by which a material can exhibit type 1 or type 2 behavior. Ginsburg Landau theory gives a ratio of the London penetration depth to the Ginsburg Landau coherence length. This is defined as a Ginsburg Landau parameter. It is usually denoted by the letter kappa, and if kappa is greater than 1 by root 2, then the material, it is energetically favorable to have such interfaces between normal, and so there can be a mixed state. For kappa less than 1 by root 2, the material exhibits type 1 behavior. In fact, both the London penetration depth and the Ginsburg Landau coherence length are can be experimentally determined, and therefore this ratio, the kappa parameter, the GL parameter, can be actually determined, and it is found that this criterion is valid in most known cases of type 1 and type 2 superconductors. So, apart from all this, the Ginsburg Landau theory also gives a very interesting method to determine quantitatively the upper critical field. For this, we should discuss what happens when you have an applied magnetic field. In the presence of an applied magnetic field, the Ginsburg Landau equation becomes we are neglecting the higher order terms involving beta and others. This is known as the linearized Ginsburg Landau equation, in which all terms except the linear term alpha psi is neglected. So, if we do this, here A is the vector potential. Now, if B is taken along the B equals B Z along the z axis, it is a constant uniform field directed along the x direction, then we can choose A, because A is del cross A is B. You have various possibilities. One possible choice is 0 Bx 0. Suppose we take this and rewrite this equation, this becomes where we have used the condition, we work in the Coulomb gauge and we assume del dot A is 0. With that assumption, this is what we arrive at. That can be written because we have only Bx in this vector potential term. Expanding this, we arrive at, in Cartesian coordinates, well, I have Ax dou by dou x ay dou by dou y and az dou by dou z, of which only ay is non-zero. So, I will write only this. So, the ay is bx times dou by dou y plus q square b square x square by 2m psi plus alpha psi equals 0, where psi is psi of x, y and z. Since we can do this by the method of separation of variables, and since this does not involve the z coordinate except here, we can straight away write the psi of z goes as e to the power I k z z, and therefore, this term can be written as minus h cross square k z square by 2m, and then we can write the remaining as psi prime x y can be written as e to the power I k y y times psi double prime x, where the primes are just used to say that psi x y z is a product. Where psi z is also of this form. So, with that we can differentiate and write the rest of the equation governing the psi double prime, and therefore, we will have minus the equation, the part involving k z factors out, and we have the rest of it written. The equation governing psi double prime can be written by the standard method of separating the variables. I will write the final result. The equation governing now, these can be written out in the form of a perfect square. So, this can be written out in the form. So, I will have minus h cross square by 2m d square psi double prime by dx square, which is in the form of a kinetic energy operator operating on psi double prime. Then the rest of it can be written in the form half m omega square x minus x naught square psi double prime equal to alpha minus, I have left out so alpha minus h cross square k z square by 2m. So, where omega is q b by m and x naught is h cross k y by q b. And in this form you can see that this is the energy which I can write as equals E dash psi double prime, where E dash is the energy, total energy minus this. Therefore, and this is in the form of the standard Schrodinger equation for a one dimensional harmonic oscillator. Of frequency omega equal to q b by m, which is displaced in center by an amount h cross k y by q b. So, the eigenvalues of energy of this one dimensional oscillator are well known. This is an exactly solved problem in quantum mechanics. So, we know the eigenvalues En are n plus half h cross omega. So, we can write now this is n plus half h cross into omega is qb by m, and that would be alpha minus h cross square kz square by 2m. So, the highest eigenvalue of this will correspond to n equal to 0 and kz equal to 0, then it becomes E0 equals half h cross qb by m equal to alpha. So, this means that the corresponding magnetic field, which is the highest allowed magnetic field, is 2m alpha by h cross q. So, this is the highest value of the magnetic field which can be sustained in a superconductor according to the GL theory. So, this is by definition the upper critical field, and this we know that 2m alpha by h cross square is already the Ginsburg Landau coherence length, the inverse of the square of the Ginsburg Landau coherence length, and h cross by q, we will see h by q is a special quantity for a superconductor. It is known as the flux quantum, as we will see shortly. It has a special notation phi naught. So, h cross by q is phi naught by 2 pi, and therefore, the Ginsburg Landau theory gives an expression for the upper critical field as phi naught by 2 pi psi gl square. So, that gives an expression for the upper critical field of a type 2 superconductor in terms of the flux quantum phi naught and the Ginsburg Landau coherence length psi gl. Now, what is this flux quantum? We can just see it in a minute. We see that the momentum operator in the presence of a magnetic field is minus IH cross del minus QA. This is the canonical momentum for a superconductor in an applied magnetic field whose vector potential is A. And we also saw that the wave function of the superconductor is a macroscopic quantum state with a wave function which goes as Ip dot r by h cross. So, this will have, writing this instead of p, I times minus IH cross del minus QA dot r by h cross. So, we can see that the quantum mechanical phase is given by the line integral in the presence of a magnetic field. The phase factor due to the magnetic field can be separately written as q integral A dot dl, the line integral of q by h cross. This is the phase shift in a magnetic field. And the line integral of A dot dl has a special significance in any system. We can transform it by Stokes theorem into del cross A dot dl, and we know del cross A is B. So, ds, the surface integral. So, this becomes B dot ds. So, the line integral, so q by h cross, and we know that the line integral of the vector potential is nothing but the surface integral of the magnetic induction by Stokes theorem, and this surface integral is nothing but what we know as the magnetic flux threading the circuit. So, this is the magnetic flux. This is a very profoundly interesting situation where we have phase change due to loop of current carrying a supercurrent loop, superconducting loop. The phase change, the quantum mechanical phase change is given by q by h cross times phi, where phi is the magnetic flux. And we know that this phase change, because this is the phase of the quantum mechanical wave function, if we go through a complete circuit and come back to the same point, the wave function should be single valued. So, this phase change should be an integral multiple of 2 pi. So, that means that phi is h cross by q n times into 2 pi, and h cross 2 pi is just n h by q. This is a very profound result. The requirement that the wave function of a superconductor should remain single valued results in a quantization of the magnetic flux threading a superconducting loop in units of a quantity called h by q. So, this quantity is known as the fundamental flux quantum. This is the flux quantum. So, the flux quantization is a very interesting automatic result of the fact that the superconductor is a macroscopic quantum state, and this is what we have used in here. So, that is the significance of this. So, the mixed state is one in which the normal regions in which the flux is penetrating contain quanta of magnetic flux threading the superconducting regions. So, these two coexist together with normal superconducting interfaces separating them, and the Ginsburg the London penetration depth is a length scale characterizing how the magnetic field penetrates the normal region, and the Ginsburg Landau coherence length tells us how the order develops in the superconducting region. So, this is the microscopic understanding of the mixed state of a type 2 superconductor. In fact, the Ginsburg Landau theory can be pushed further, and the linearized Ginsburg Landau equation can be written in the neighborhood of T c when the order is very small. So, we can linearize the Ginsburg Landau equation because the change in the order parameter is extremely small. So, it is a small quantity. So, the expansion and truncation with the linear term is perfectly justified. So, if we solve the linearized GL equation, this solution was carried out by a person called Abrikosov, and this solution he showed results in the creation of a flux lattice in a type 2 superconductor in the mixed state, and he showed the condition for the stability of this flux lattice, and all electrodynamic behavior and characterization of a type 2 superconductor for applications such as making high field superconducting magnets. We have to know the nature of the flux lattice and how the periodicity of the flux lattice and the structure of the flux lattice in order to go further. So, this is the reason why I said the Ginsburg Landau theory provides an insight and a guideline for describing a real practical type 2 superconductor, which is of real interest in technical applications. Well, it is not just the full story. As I already said, we have also soon afterwards a microscopic theory was developed by Bodin, Cooper and Schrieffer. We called it the Bcs theory, and for a long time the Ginsburg-Landau theory was developed by Ginsburg and Landau inside the Soviet Union, and the Bcs theory was developed in the United States. And for a long time, because of Cold War situation, there was nothing known on either side of the Iron Curtain about what happens in the other side. And then nobody knew whether the Ginsburg-Landau equation is correct or the Bcs theory is correct. And it was left to a person called Gorkov to show that both theories are really mean the same thing. He adopted a Green's function formalism in order to establish the essential equivalence of the GL theory with the Bcs microscopic theory. So, we now call the GL theory as GLAG theory, Ginsburg, Landau, Abrikosov, Gorkov theory. So, in that form we have a fairly unified understanding of both the microscopic and the thermodynamic behavior and the electrodynamic behavior of a superconductor. We will consider the microscopic theory in the next lecture.